Chapter 6, Trig 2. So, bless you. This uses a lot of Chapter 4 in Chapter 6. So, like when you do that, what you just wrote a test on. So, like cos of 30 degrees or secant of 7 pi over 6.
But no drawing?
No. No drawing. Okay. So the first thing we're going to talk about is a few formulas on our formula sheet. So these are called the Pythagorean theorem identities. Your first one is this top one up here. The sine squared plus cos squared equals 1. Do you see it? Okay. What's cool about the sine squared plus cos squared x equals 1 is it's just the unit circle formula. Because sine is y, cos is x, equals 1 is the radius, right? So it's just, you wouldn't even need it on there because you already know it. Sine squared theta plus cos squared theta equals 1. Now, how do I get that into any other form? What could I do? I could subtract what? Either the sine or the cos. So if I subtract the cos, then I could say sine squared theta equals 1 minus cos squared theta, correct? And we're going to be using these in a little bit. So if we ever see 1 minus cos squared theta, we can toss it behind our heads and replace it with sine squared. Or if we see sine squared, we can toss it behind our heads and replace it with 1 minus cos squared. Most often, you're replacing 1 minus cos squared with sine. This happens in proofs. So we could also have subtracted the sine, and we'd have cos squared theta equals 1 minus sine squared theta. The people who do really good in this unit are the people who know what formulas are on that formula sheet. You don't have to memorize them because they're there, but often people won't even try to learn what's on them, and then they don't even know. I know if I see 1 minus cos squared, I can immediately replace it with sine squared because I know that's a variation of what's on the formula sheet. If you don't know that, though, you'll just sit and stare at the question and be like, I don't know what to do next. So the people who know what's on that formula sheet on the right-hand side, because basically Chapter 6 is the whole right-hand side of that formula sheet, do much better on this test. So the next one is it's tan squared theta plus 1 equals secant squared theta. Basically, if you take this formula and you divide it by cos, I'll show you down here. Don't write this. I'm just going to show you how we get that. Don't do this. It'll be confusing. You'll be like, where the heck did that come from? But if I take the sine squared theta formula and I divide it by cos, every single term, cos squared theta. This becomes what? This becomes what? And this becomes what? So this formula is the same as that formula. They just took a divided by cos squared. Okay? So how can we vary this one? I'll just leave this as a little bubble. What could we do to change that one up? Subtract a tan, so you could have secant squared theta minus tan squared theta. That one's not used as often. There's another one that is used more. Subtract the 1. So we have tan squared theta equals secant squared theta minus 1. So if I ever see secant squared theta minus 1, I can toss it out, and I can replace it with a tan squared theta, right? Okay, there's a third trig identity, or Pythagorean theorem identity. And so if I take sine squared theta plus cos squared theta equals 1, and this time I replace it with, or I divide it by sine squareds. This time, what am I going to get? 1 plus cotan squared theta equals 1 over sine squared is cosecant, right? Squared theta. So that's the third one on your formula sheet. You don't have to show how you get them. I'm just proving a point that the first one is the unit circle, and then it's just varying ways of the unit circle. Now, what could I do here? Subtract the cotan. Don't know why I'm showing that step. I'm going to just write the next. 1 equals, switch. Cosecant squared theta minus cotan squared theta. Or what's my third option? Yeah. Cotan squared theta equals cosecant squared theta minus 1. Do those make sense? It's just varying of moving the 3, and they're all from just the unit circle formula. Okay? The next thing we're going to talk about, so that's the formula we use in this lesson, those 3 formulas. Next thing we're going to talk about is non-permissible values. Is it permissible? My brain is stopping. It's halted. I don't remember. I think it's an I. It is. It's an I. It looks stupid. That's what I thought. Permissible. That still looks stupid, but it's right. Value. So non-permissible values you talked about in grade 11. Do you remember what they are or why they exist? What the heck is that? They also are called restrictions. Yeah.
It's usually because you can't have like 0 in the denominator because anything divided by 0 is undefined.
Is an issue. It's like no-go, right? It's illegal in all states, territories, provinces, in Europe, all over. You're not allowed to divide by 0. Yeah. So you're not allowed to divide by 0. Now, if it's just numbers, you have no problems. Like if your denominator is 7, well, it's not 0. Yay. If your denominator is 17, woohoo. If your denominator is 4, yay. Like you have no problems, right? Problems happen when you get a variable in your denominator. That's when problems exist. That's when you get non-permissible values. Because the moment you have a variable in your denominator, let's pretend we go back to grade 11. And we had like 3 over x. Or we went back to this year. What happens? We have to state x can't equal 0. Because if it did, my denominator is done. Yeah, I heard 0. That's what you said the whole time. Totally. So x can't equal 0 because it would make the denominator 0. We agree? Well, now we're just going to trig in the bottom, which is like, you think it's bad. It's not. These are not the bad things. I promise you. Reserve your judgment. Okay? Reserve your judgment. The class is all right. So, if we have an example, sine x over cos x. What's my issue? Cos x can't equal 0. Problem, right? So we go, cos x can't equal 0. And then we have to state all the places where it does, and we're like, no x, you can't equal that. Because restrictions are x can't equal, and then I give values, and then I'm done, right? That's what restrictions are. X can't equal something, correct? So I need to find out all the places where cos x equals 0, and then state those x's. So, where does cos x equal 0? 90 and 270, etc., 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 and then backwards, etc., etc. There's a whole bunch of places, correct? So what am I going to have to state when it's a non-permissible value? General, unless they give me a restricted amount, a restricted domain, and say what are the non-permissible values, right? Other than that, you have to state general. So how do I state a general? I'm going to do it in degrees first, then radians. So how do I state a general? X can't equal, what's my first one? 90. So I always look for my first positive. And then what am I going to do to get to the next one? 180 degrees. N. And then what? Any I, because it has to cover all the positives. and the negatives, because if I plug in 0 here, I'm going to get 90. If I plug 1 in for n, I'm going to get 270. If I plug negative 1 in for n, I'll get negative 90, right? And I'll get every single one just by plugging integers in for n here. Okay? Yay, good job. Okay, in radians, that's pi over 2. I'm trying to say radicals, even though we're not in that unit. Bless you. So they keep coming out as radians and stuff like that. Okay. Boom. Example. Okay, new example. I don't know where I'm going with this. I need to stop. Nope. I'm going to go like this. 1 over cos x. I really wanted the cos in the bottom, but started writing it in the top. It was, oh, no, I do want it in the top. I do want it in the top. Ah! No, I want a sign in the denominator.
Cos over what?
No NPVs. Okay. I wanted a sign in the denominator, and I didn't want a funky like cosecant or something, because that causes more NPVs. So I was trying to draw it, like, but it will. It's there. It's there. Okay, we got there eventually. What's my problem? Yeah, I couldn't believe you could figure that out when I said I'm trying to get sine at the bottom. Yes. Okay, signs are issue. So we know sine x can't equal 0. If it does, I have problems. Correct? So where is sine equal to 0? Where y is equal to 0. And where is y equal to 0? 0, 180, 360, negative 180, negative 360, blah, 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 blah. Right? So where's the first positive one? 0. So x can't equal 0. Now you know it can't. If you type sine 0 degrees into your calculator, if you type that in, it's going to go 0. And you're going to be like, oh, can't divide by that. That's a problem. That's why that one's out, right? If I plug in 180, sine 180, it'll go 0, which is the problem, right? Your calculator would fight you, literally. I wish it would. You'd stop doing it then. Like just slap you. All of a sudden get, whoa. Oh, your calculator. I get it. Okay, so what do we add to get to the next one? Your reflexes would be super better. Yep, like my English. You're welcome. 180 degrees and NEI. But what did I tell you to do when you have a 0? Or what did I tell you they won't do?
Put it in.
They won't put it. This will just go, gone. So we're going to go 180 degrees and NEI. Or pi and NEI. Okay. Exemple 3. I don't even... Exemple 3. There we go. I didn't have any more words. It's a short wrap. Okay, so we have sine x over tan x. What's the problem? See? Very good. You learn well, grasshopper. I sounded like a seal. You sounded like you were dying. Okay. Tan x in the denominator. So, what is tan the same as? Yeah, there were so many answers, so little time. Okay, so if I get this, watching, please, this is going to be a mental note. We're going to take this with us after this moment. It is going to be part of your toolbox. Okay? So, we have sine x over 1. You can bring your real one in if you really like. We're going to divide by tan, which is sine x over cos x. Why the heck did I write this sideways? Because do you ever stack fractions? Do you go like fraction divided by fraction and stack them? Is that helpful? That is not helpful. If you are doing that, stop it. Okay? Terrible. That is something you need to stop immediately, if not sooner. Okay? So, sine x divided by sine x cos x. Whenever you get a fraction over a fraction, stop yourself and write them sideways. If you do that, proofs will be easy. If you don't, it's really bad. Not even slightly, it's going to be real bad. Okay? Nothing's going to come out good. Bad. All right? Stacking fractions should be illegal. It should immediately flop to the side. Like you should be trying to stack it, and like your pen should fly away or something until you write it sideways. Yeah, slap you as well. Things like that. All right. So, in rationals, let's go back to grade 11. When you had an A, a B, divided by a C, and a D, voila. What did you state non-permissible values of? I heard it. The B and the D, and someone else said the C. Because this is going to come down here after we multiply, after we do the reciprocal, and it's going to move up, correct? So when it is a division, do you see that? We state non-permissible values of both denominators and the top right numerator. I was thinking left because I'm facing the left, but that is not true. You're right. Okay? So, what are we going to state non-permissible values of? 1. Done. You're welcome. That was easy. What else? The cos and the sine. So we have to state where sine x can't equal 0 and where cos x can't equal 0. Okay? So, where is that happening? So cos x is 0 here and here. So cos x is 0 here and here. Sine x is 0 where y is 0, so here and here. So I'm going to actually lump them together. Why am I going to lump them together? To make it shorter, because I'm lazy. That's why. Also because it looks prettier. So, if we didn't spot the sine and the cos, if your tan was in the denominator, you have to find the places where tan is equal to 0. Now, where is tan equal to 0? Where y is equal to 0, because it's 0 over a number, correct? So tan is equal to 0 here and here. Because you do y divided by x, we agree? And then people are like, but there's more. Why? At 90 and 270, what happens on tan graphs? You get an asymptote. So can it equal an asymptote as well? Can it equal it does not exist? No, so that's why it's every single arm. But I always switch everything to just sines and coses and deal from there, because it's just easier for me to visualize that. Still all the arms. So I would say x can't equal, what's my first one? 0 plus 90, n, degrees n, NEI, which we know we don't write the 0, so it's going to be x cannot equal 90 degrees n, NEI. Or, in radians, pi over 2, n, NEI. What happens if there's a cotan in the denominator? Cotan is just cos over sine, isn't it? So I would still have a cos and sine on the right-hand side. So what would my non-permissible values be? The same. I would just have a cos over a sine here, right? Cotan wouldn't change anything. Okay, what they can do as well, though, is they can do this. Sine x tan x over cos x minus 1. Looks more difficult than it is. My first suggestion when it says... Yeah, that's a multiply. Sine x tan x. Just stop. Halt. Okay, the first thing you want to do, 9. Okay, the first thing you want to do is you want to turn everything to sines and coses where possible. That will help you, right? When we changed the tan to sines and coses, it was helpful. If we would have taken our cotan, we would have changed it to cos and sines, it would have been helpful. So the first thing I would do, because you have to see if there's more denominators. I know the cos x minus 1 is a denominator. I see it. Here it is. Hello, there you are. But this can create more denominators. So you have to change it to sines and coses. So watch what I'm going to do. I'm going to go equals sine x, technically over 1, isn't it? Yeah, everything is. And then tan x is what? Sine x over cos x. Holy smoker doodles Batman, I have a fraction in the numerator. So then I should just write this underneath. Do I double stack fractions?
Yes, do that. Last picture.
Never. Oh my Lanta. No. So how I help myself out is I will put the numerator in its own bracket and the denominator in its own bracket so that I know, hey, left is a numerator, right is a denominator. This is just the top. Divided by this is just the bottom. I haven't done anything crazy. Because they're multiplied. No. There's no sign, so it's a multiplication. Good talk. All right. So, we agreed that we state, when it's a fraction divided by a fraction, we state non-permissible values for this denominator, this numerator. We agree? All right. So what's our denominator on this side? Cos x. So we have to state where cos x can't equal 0 for this one. And then for this one, what do we have to do? Cos x minus 1 can't equal 0. So where cos x can't equal 1. The key to teaching AP is trying to answer before you answer. Like, cos x 7, 9, 2, 7. Yeah. Mm-hmm. Yeah. Throwing out answers all the time at me. I'm like, ugh. And Lepp, it's like 90 plus or minus 75. I'm like, I'm still up here. Where are you going? Yeah. All right. What is this one? Not 13. Where does cos x equal 0? Where does x equal 0? 90 and 270. At 180 it would equal -1, and at 0 it would equal 1, right? So we've picked these ones. So we're going to do it just in degrees this time. X can't equal 90 degrees plus 180 degrees n NEI. Now just so you know, if they say it's in radians, you have to put it in radians. If they give you a restricted domain in radians and you give me an answer in degrees, no, not good. Bad. Okay? Where does cos x equal 1? 0, 360, da 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 da. So how can we just write it? In degrees. 360 degrees and NEI. Don't forget the degree symbols, guys, like I did on the test. NPVs make sense? They're not cray-cray. Turn everything to sines and coses and put your fractions aside to do not stack fractions. Yes?
So do you just like combine the x can equals like when it's convenient?
Yeah. Yeah, that's as good as it gets. You can't combine these.
Yeah.
Yeah. Okay. Now we're going to do verifying.
Right.
Yeah. That's what verifying is. Thank you. Okay. So we are going to verify. Now, these are your steps for verifying, and you cannot do them not like this. It will go poorly for you, meaning they'll give you no marks. So, 1. Set. Yeah, I made it still negative. Set up a T-chart. Oh, shush, you guys. It's literally a left side, right side. You'll be fine. Okay, 2. Write the exact formula in question, in the question, in the T-chart.
T-shirt.
Oh my gosh. Chart.
We're on a roll.
Yes, we are. It's mainly me. Okay. 3. For 3, this is the important part. So you're going to write a T-chart. You're going to write a T-chart. You're going to fill in left side into left side. You're going to fill in right side into right side. Then in the third step, you will immediately, yes, because people don't do this and then they get 0 on this. Immediately substitute Okay, quiet guys. Substitute in your x value. Which your x value could be a theta, or it could be whatever. It's not always just an x, right? It's just a variable. It could be an n, it could be an n, whatever. And then go to your unit circle. Make left side equal right side. And then you're done. Now, the reason why number 3 immediately substitute in is because you guys will write the formula and then you'll start changing things. You'll see a tan and you're like, oh, that's sine over cos. No, you're not allowed to do that. If you see a tan, it's a tan, and then you write tan of 30 or whatever it is. You can't change anything. So you guys will put like a version 2.5 step in here. The moment you do 2.5, that 2.5 step where you start adjusting stuff before you substitute in, it's a proof, not a verification, and you get 0 on that question in a written response. And people will say, well, why? That's rude. Well, it's a proof, not a verification. You're asked to verify, not proof. So you're actually not doing, it's like someone telling you to run up the stairs and you run down them. It's the complete opposite. It's not at all what you were asked. Okay? So,
Isn't this like an extra thing concerning our answer? They'll actually ask us to verify.
they'll say verify, and they'll make you verify. A verification shows that for one value it works. A verification, if you verify 5 values, it shows for 5 values it works. It's not a proof, it's a verification. So they can ask you to verify. And honestly, verifications are done the worst. They're the easiest to do, but people will put a 2.5 step in there and it's immediately wrong. So there isn't one. There is no 2.5 step. Don't make one. Okay, verify that sine x tan x equals cos x. This one is not an identity using A, x equals 45 degrees, B, x equals 30 degrees. When they ask you to verify, if they say verify this, you're verifying it works. So if they ever say verify this, left side will equal right side. If it doesn't, you messed up. Go back, try again. Okay? If it says verify this, it works. People say, what if it doesn't? You're wrong. Go back. That's the only way it's not going to work. So these ones say verify that this is not an identity. Now what I wanted to prove with this is that something is an identity if you can use a proof and never plug anything in for x and show that left side equals right side by plugging in some formulas, which we're going to do soon. Verification only shows that for that value it works. Now how you can actually prove something doesn't work is by getting one counterexample. One counterexample, one example where it doesn't work, left side doesn't equal right side, will immediately prove that this is not a proof and it doesn't work. You only need one counterexample to show that it's not a proof and it does not work. But you need to actually never plug in a verification value if you want to prove it works for all values. So this is just a verification. So we're going to try 45. You can't plug these into your calculators. That's not a verification. So what was the first step? Make a t-table. Or t-chart. So this is left side. This is right side. So you label it LS, RS. The only thing you can short form, enjoy it. You can actually go LS, RS. It means left side, right side in math. Okay, our next step is we can write the equation, the left on the left, sine x, tan x, cos x. We agree? That was step 1. Step 1 was table. Step 2 was writing that in. Step 3 was immediately plugging in the value. Don't change tan to sine over cos. Don't go doing anything. The moment you change this to sine over cos, you have no marks. Just so you know. Because that's not a verification. You're verifying something totally different. If you change this to sine over cos, now you're verifying that equation. Is that what I wanted you to do? I want you to verify this one. So, we're going to go sine 45. Our third step is to immediately just plug in. Sine 45, tan 45, degrees, cos 45 degrees. So your first step is rewrite the question. Second step is plug in the values. Don't doctor anything, don't change anything, just plug them in. Then your fourth step is to go to your unit circle. What is sine of 45? So go to 45 and it's the which?
Root 2 over 2.
Yeah, it's root 2 over 2, it's the y. So this is going to be root 2 over 2. What is tan of 45? 1. Every 45 is either for tans or cotans is either 1 or negative 1, right? It's positive 1 in quadrants 1 and 3, and it's negative 1 in quadrants 2 and 4. Yeah.
Will it always be exact? Like
When they ask you to verify?
values, like
Yeah.
special items?
Yeah. And so then this is 1. And then cos 45 is root 2 over 2. So now I have, people will say left side equals right side. I'm sorry, unless my kid in grade 2 or 5 could look at this and say they match, you're not done. So if my kid looks here, they're going to be like, I have no idea what that is, but that does not look like that. Okay? You have to have a little wee child be able to look at it and be like, they look the same. I have no idea what they are, but they look the same. So right now, they don't. So I have to go root 2 over 2, and then this is root 2 over 2, and now I have a little wee child that goes, ah, they match. And then you go left side equals right side. If you can't have someone who has no clue what the heck you're even doing say that those are match, you're not done. So people will go here, they match. No, they don't actually. I don't know how you think they do. That if I picture, if this was an image and this was an image, you guys would say there's very things, this one is different. Right? You can't just be like, oh, they're the same. The person who's doing this now can see that it's a proof. No, you can't be like, oh, the person from here to here can verify in their heads. If they have to do math to verify your thing, it's not done. Okay. Yeah.
Do you have to use the t-chart?
Yes.
Like
For Trig.
Can I get a mark for the teacher?
You're going to use the t-chart because you're going to use the t-chart in a proof as well. So the thing is, if you use the t-chart, you don't actually have to have the same amount of steps on the left as on the right. If you use just equal signs, which is okay, if you use just equal signs, you have to carry the equal signs down the whole time. So you always have to have a right and a left. Always a right, always a left, always a right, always a left. Sometimes a proof, for example, might be a t-chart like this, and you might have a whole bunch of steps down here, like this many, and this will be sine x. And then you'll down here, you'll have sine x, and then they'll match, and you'll go left side equals right side. So if you go with the t-chart, you won't have to write both sides down the whole time. I always used to do it without the t-chart, but then I got lazy people, and I didn't realize they were going to just be lazy, and they'd go like this. You go sine x equals, and then it'd be like sine x cos x blah 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 information, and then they'd go keep going the information down here, and then eventually they oh yeah right sine x, and then they keep going, and then the moment you don't write this sine x the whole way down, you've not done a proof or a verification. So you have to have a left side and a right side and every single equal sign if you don't do the t-table. And trust me, I see this way more often, or like an arrow, or some like ditto signs. I'm like, stop. It has to be like what it actually is. So I have switched to this only because basically laziness makes people not write the thing down the other side and they lose marks. So like it's not proof. So you can do this totally. But you always have to have a left, right, left, right, left, right, left, right, left, right, the whole way down. The moment you drop off a left or a right at all, you've completely thrown out the verification or the proof. It's just that. So, I accept either if they're correct. Like, correctly done. You know what I mean? But you can do that totally fine. I used to only do that. And then people didn't write their left and right sides down. So it's just that. Okay, 30. So for right now, we know that it worked for 45. People will say, proof, it's done, we proved it. There we go. That works for everything because it worked for 1. Does that even make sense when you say that statement? No, it's not true. Just because it works for 1 doesn't, even if it works for 4, doesn't mean it's going to work for them all. So let's try this one. 30. So we have to rewrite sine x, tan x, cos x. So we're going to go sine 30, tan 30, cos 30. What's sine of 30? 1 over 2. What's tan of 30? Root 3 over 3, because all the 30s are root 3 over 3s, or negative root 3 over 3s, and all the 60s are nicely root 3s, remember? Cotans are opposite. And then cos is root 3 over 2. And then I have root 3 over 6. And I don't have to rewrite this one down here, right? That's the key thing about the t-table. Once you have like the sides, you don't have to follow them down like an equal sign. And then this would be left side does not equal right side, which immediately disproves this proof. So one counterexample can throw the whole thing out. If you find one that doesn't work, you can throw the whole thing out. If you find a million that work, it's still not a proof. If you find a billion that work, it's still not a proof. The only way you prove something is if you never fill anything in and you just use x's. And we just use formulas off our formula sheet to get them to match, to be like sine x equals sine x or something like that. Okay? So verification is a one value thing. It proves for that one thing that it works, so that's it. Or if you can prove for 100 that it works, but it doesn't prove that for everything it works. But a verification can instantly prove something doesn't work. Okay. So those are verifications. Does that make sense? You have to plug in immediately and get your left side to equal your right side. You write the equation, plug it immediately, use unit circle, boom, boom, boom. Okay? What is a proof? So, a proof is you never substitute a value in for x. And you use formulas off your formula sheet. And in the world it would be, but ours is formula sheet. To substitute in. Until the left side equals the right side. At no point do you fill a value in for x. So before we do proofs, we're going to do some simplifications. So we're going to simplify. Cosecant x minus cos x cotan x. This isn't a proof, and I can't verify anything because there's no equal sign, right? I'm just simplifying one side of a proof, basically. These are all singles. Do you see that? None of them are squares? Okay. What I need to send home into your heads with you here is any singles, you immediately look at the very top. These are all singles. Do you see them? Cos be cosecant, or sorry, cos be 1 over secant, oh my goodness. Cosecant is 1 over sine, etc. This is what I need you to pay attention to. Do you see these Pythagorean theorem identities, how they're squared? You can only replace them with squares. But the singles, you can actually replace with squares as well. Let me show you something. So the singles can only be replaced with singles, we agree? But the singles can actually become squared. So for example, what am I saying? I'm saying that cosecant squared x, let's pretend, because I don't have a square here, I'm just teaching you early. This can be written as 1 over sine squared x. Now, why is that? Because a cosecant x is just a 1 over sine x, isn't it? So a cosecant squared x is just cosecant x cosecant x. So that's just 1 over sine x times 1 over sine x, which is actually just 1 over sine squared x. So these single ones up top can actually be replaced with squares as well. But the squared ones cannot. You can only do a squared for a squared. Like a secant squared, you can't go, oh, okay, instead of secant squared, I'm going to put 1 plus tan. Can't do that. That's illegal everywhere. So you can't, because you have to take the square root of secant squared, which would take the square root of 1 plus tan squared theta, which is not 1 plus tan. Okay? So the singles can be squareds, but the squareds can't go down to a single. You have to like physically square root 1 plus tan squared, which is not what you want. So these are all singles. Where's the only place I can go? off my formula sheet. Your formula sheet's going to be your bestie for this whole unit. So what's cosecant? 1 over sine. Now we're simplifying, so this is going to equal the next one. Simplification, when you don't have an equal sign, you run an equal sign down the left. So cosecant is 1 over sine x. Minus what? And then what's cos? Well, it's cos x. Over what? Over 1. What's cotan? So some people will say 1 over tan, but that's not helpful. We try and switch it to as much coses and sines as possible. So yes, cotan up there is also cos x over sine x. Then I want to simplify it out, so I go 1 over sine x minus cos times cos is cos squared x. Remember, the squared falls in the middle, not at the back. That would be an x squared. When the squared's in the middle between the cos and the x, that means you have 2 coses multiplied together, like a cos x and a cos x, over sine x. Now, what do these both have the denominator of? Sine, so they have a common denominator, correct? So I can just write 1 minus cos squared x over sine x. Does anyone know any formulas off my formula sheet that could substitute out here? The top Pythagorean theorem identity. Yep. The top Pythagorean theorem identity is, that's why I said you need to remember that you have variations and you need to memorize your variations. Sine squared x plus cos squared x equals 1, correct? If I subtract that cos squared x over, I get 1 minus cos squared x. So what can I actually replace 1 minus cos squared x with? Sine x. It's like a puzzle. So I get sine squared x over sine x. And sine squared x is just what? A sine x times a sine x, correct? So I can do this. Cross 1 off for 1, and I get sine x. Now this would have NPVs wherever sine x equals 0, right? If they ask me for non-permissible values, because that's my denominator. Yep. The denominator isn't sine x squared. The numerator is 1 plus 1 minus. I just did this. You just rearrange this. You get 1 minus cos squared.
Yeah.
So the 1 minus cos squared became sine squared.
Okay.
The denominator is still sine. I didn't change anything to it. So it's just rearranging that Pythagorean theorem identity. Okay, example you're going to try. Simplify.
So it's simplified?
No, simplifying. Simplify just means you have something that's larger and you need to make it smaller. That's all it means.
Part of the question.
That is how my daughter defines things. She's like, oh, what was it? Oh, climate change. Climate change is when the climate changes. I was like, you can't. She's like, well, I was like, no. Well, she is, because you just used the definition in the definition. It's like, I said to her, that's like, if you said, how do you wash dishes? Well, you go there and you wash the dishes. I was like,
Well, that's not wrong.
She's not wrong, because everyone knows what wash the dishes. Everyone knows more elaborate.
it's climate change. That was the definition of her curriculum. You can't define it with climate change again.
When the weather changes.
No,
That's climate change.
that's not climate change.
Of climate.
When the weather changes over a large period of time, at least 30 years, is climate change. Why do I know that? Because we have to look up the real definition, because her definition sucked.
We can file a complaint.
No. Her definition sucked. The teacher's didn't. I looked it up and found the teacher's definition, which was not my daughter's, which was climate change is climate change. So the climate change. All right. Oh, I've been, goodness gracious, I've been,
She's waiting for nobody. She's on our wall.
So you're going to get sine x over 1 plus cos x over sine x times cos x over 1. So I'm going to get sine x over 1 plus cos squared x over sine x. And what's my issue?
They don't have a common.
Not a common denominator this time. So I'm going to multiply by sine x. And so I'm going to get sine squared x over sine x plus cos squared x over sine x equals sine squared x plus cos squared x. And what is sine squared x plus cos squared x? It's a 1. Really large 1. So I get 1 over sine x, which I could actually, if they asked me for a single trig ratio, I could say cosecant. So 1 over sine is acceptable, but if they ask me for a single trig ratio, that's cosecant.
If they don't answer that, you just simplify.
So 1 over sine is fine.
I didn't much. I didn't exactly. I didn't much.
Okay, so yes, so that is one thing that you guys are going to have to stop yourselves from doing, because that's the only thing about 98% of the problems that happen in proofs is canceling off too early, and 98%, no joke. So whenever you have a plus or a minus sign, I'll always try and slap them into brackets so that people can't, like, so if there's a plus sign, so it sews these together. So the only way that sine squared x plus cos squared x is going anywhere is if there's a matching sine squared x plus cos squared x on the bottom. So the moment there's that plus sign in between, they're sewn together, and that's like one entity, and the only way it can go away is like if you can take a GCF out of it, or you could factor it, or you can completely cancel it off as the exact same thing. But people will try and do this. You can't. That's like chopping the head off of a person. Like this is a whole person here. You just chop its head off for like a body. Don't. That's bad. It's so bad I'm going to press arrows to go back. Okay. So you can't do that because of the plus sign. So you have to watch yourselves, and sometimes the way to stop that, I found, is brackets. Okay? So we're going to try this. Example. Cotan theta, which is going to cause you to have a stacked fraction. So will you keep it that way?
Yeah.
No.
It looks cool.
The definition of a stacked fraction is a stacked fraction. Stealing. Cosecant theta minus sine theta. You're going to try that one, and then you're going to simplify this one. Tan theta over secant theta minus cos theta. Try those two. Just start working on them, but you can keep trying yours.
We're going to try.
Okay, look here for a second. So, all I did was change everything to sines and coses at this point. And do you see how I put square brackets so that I know what's numerator and denominator? The other thing, division can only flip when you have a fraction divided by a fraction, full fraction. So if I have like a over b divided by c over d, I can flip this and multiply. We agree? But if I have like a over b divided by 1 over c plus d, what am I flipping? I don't know. That's a problem. But you guys will flip things. You just flip them all over the place. Like you look here and you're like, that's stupid, I can't do that. Then here you'll be like, I flip. And no, you don't. So you have to note, that's why I put the numerator in a square bracket and the denominator in a square bracket, because those square brackets have to be full fractions, and then boom, flip. Great. Awesome. But if those square brackets are not full fractions, you can't flip. You can't. You can't just flip this first half and then leave that, or whatever you think you should do. Don't do any of that. It has to be a full fraction in the square, full fraction in the square brackets, then flip. Okay? So, I need a common denominator. I need to times this one by sine theta and sine theta. So, now on this side, I'm just going to let it sit because I have nothing to do with it. Cos theta over sine theta divided by 1 over sine theta. I'm not going to skip steps, but you could have skipped this step. Sine squared theta over sine theta. Because they're common denominators, you could have just skipped the step and wrote the whole numerator over it, right? But I'm not going to. So I'll have someone stop me if I don't. So cos theta, sine theta. Still not flipping anything because I still don't have full fractions, do I? Nope. Keep going until the square brackets are full. So I get 1 minus sine squared theta over sine theta. Holy smoker doodles, Batman. I now have a full fraction divided by a full fraction. I can say what I want when I want.
Yeah. And it's this whole thing.
I've been saying it for like 10 years.
Did your family steal it, Grant?
No.
No, it's a saying.
She's been
His whole life, probably. Okay, so then, what can we do? Flip. So we get cos theta over sine theta times, you don't have to put in square brackets because some people freak out. They're like, I don't like those. Then don't. I don't care. Sine theta over 1 minus sine squared theta. What can I do? I can replace this bad boy with cos squared theta because there's no plus or minus signs and because it's a multiplication. Boom, boom. If this was like sine theta plus cos theta on the right hand side, I couldn't do this. Correct? If there was a plus sign and like a 1 or something on here, I could not cancel them. I can only cancel them because they're just multiplied. And so then I'm left with a cos on here, and this one cancels one of these off. So what's on the numerator? A 1, because these little things are actually just nicely slanted ones. So that's 1 and 1, so it's 1 over cos theta, which is secant theta. Fun times. You're all invited. Okay, this one, tan theta is sine theta over cos theta divided by secant is 1 over cos theta minus cos theta over 1. What do I need? Common denominator. So I'm going to multiply by a cos theta and a cos theta. So I'm going to get sine theta over cos theta. And then on the top I'm going to get the division sign. Oh gosh, I'm just going to erase that. Oh, erase so much. Why did you do that? Divided by, in case you don't like square brackets, I'll do round. I don't care. 1 over cos theta minus cos squared theta over cos theta. And then I get sine theta over cos theta. Divided by, it's really tiny division, 1 minus cos squared theta over cos theta. And now, because they're full fractions, I can actually flip, invert the right-hand side. So sine theta over cos theta, and then cos theta over 1 minus cos squared theta. Invert and multiply what you're dividing by. Thank you, Mr. Tetlock, circa grade 7. All right. Neg 1 minus cos squared becomes a what? Sine squared theta. The coses cancel, the sine and the sine squared cancel, and I'm left with 1 over sine theta, which is cosecant theta. Okay, next one. Example. Sine squared theta, still simplifying, 1 plus cotan squared theta. Cotan squared theta, cos squared theta minus 1. So we'll do the first one together. there anything anywhere on a formula sheet that can help me out with this situation?
Yes.
What?
It's
The one. It is a good one. Yes. The third one is, by golly, what's on there? Isn't it crazy? 1 plus cotan squared. 1 plus cotan squared. Take that baby in. Toss it out and replace it with what? Cosecant squared theta. And what can I do? Yeah, it's reciprocal. So it'd be sine squared theta over 1, and then cosecant squared is 1 over sine squared theta. Oh my goodness, what's going to happen here? The world is real. Everything cancels. Second one's a little different because people want to replace cos squared theta minus 1 with sine. It's 1 minus cos squared. So if I want cos squared minus 1, how do I rearrange that formula? I need to have sine on the other side and move the 1 to this side, correct? So the formula I'm dealing with currently is sine squared theta plus cos squared theta equals 1. But I need the 1 to move over here. So I have sine squared theta plus cos squared theta minus 1 equals 0. And then what would I have to do? Subtract the sign. So I can't replace it with a positive sign, but I can replace it with negative sine squared theta. Yeah, you're supposed to. Not only is it worth it, you should. Okay. So cotan is what? Cos theta over sine theta. Now some people will want to change it into the convoluted one with a minus 1. Have you gotten any closer if you changed it to that? No. No. Like the only way you want to replace it with like a cosecant squared minus 1 is if you need like a difference of squares. But like 1 plus cotan gets you further away. So this is cos squared over sine squared. And then this one is negative sine squared theta. And if you don't know what to do, replace this right one and then be like, hey, what would be better to do with this cotan squared? Oh, if I make it just be cos and sine, things will cancel, right? So you know to fill this one in, do this one first then look at this one and be like, what would be the best way to replace that? Oh, just replace it. So then these cancel and I'm left with negative cos squared theta. Okay, you're going to write some down. Are you ready?
No. No, you get 13.
We're going through these at the beginning of class tomorrow, so I'm going to walk around and check them.
Are they true?
They're simplified.
We've not really improved yet, so don't get that improved. The way we did.
Was this proofs or was it simplified?
No, this is simplified.
There was no proofs. There's no left side. I mean, there's no right side. There's no left or right side. There's no equal sign. There's no sign.
It's simplified. It says simplify it, but not except for you.
It can't be a proof. If proofs have equal signs, I decided to go to the textbook instead. Well, then you don't have to write them down.
Then like the mental block.
I believe in you.
No.
I do. Okay. She doesn't even believe in herself.
Oh my gosh. How long have you been doing it?
To be fair, it wasn't just absolutely correct. I forgot to put my phone
That didn't make it better.